Hi. So the goal of this presentation is to give you my view on how one might write something like an NSERC proposal. This is also related to thesis proposals in fourth year engineering science, which are modeled in their format, at least, on NSERC proposals. So a little bit about NSERC proposals. Canadian permanent residents can apply for NSERC. So PGS is a little bit less money. CGS is the fancier one. So in most cases, NSERC scholarships would increase your graduate stipend by some amount, sometimes by quite a lot. Depending on which university, which department you're going to, the exact amount will vary, but it's always good, and it's good for your resume later on as well. So the proposal itself is a research proposal. However, there's no commitment really to work on the exact proposal you submit. Everyone understands that plans change. If you have your entire research planned out and you know that it's not going to change, well, it's not really research because you already know how it's going to work out. So for University of Toronto students, this would be the link to go. You can just Google it as well. So what's a good NSERC proposal? I'll answer cynically first. Like, a good NSERC proposal is one that gets funded. Everything else is kind of secondary. A little bit more seriously. So various people review those proposals. So this would be university faculty, but also other people, and they will have various opinions about what's good. It's an inherently subjective process. You don't know. There's definitely some luck involved in terms of getting funded. Sometimes you write a good proposal and your application is good, but you just get unlucky and it doesn't get funded. And of course, a lot of other aspects of the proposal, of the applications rather are very important, not just the proposal, which in fact could be a quite minor factor. So the reference letters matter, the resume matters, the grades matter. So all of that matters, possibly more than the proposal. With that said, a lot of those things are already fixed by the time that you're writing your proposal. The proposal is your opportunity to increase your chances. Why am I qualified to talk about it? Well, maybe I'm not. However, I did on one occasion write an NSERC proposal that did get funded. So in that way, I'm qualified, although it was quite a while ago. And I should say, I definitely also got lucky. So I have not read them, but I assume I got strong reference letters from my mentors. My GPA actually was quite low. So by the standards of today, very low. I probably would not have gotten into grad school. So for the record, my grad school GPA was actually very good. Although arguably in grad school it's easier. So I'll give you my view of how to do it. And I want to acknowledge there are different ways of writing those things. My way might not be the best way. It might not even be a good way. However, it did work out for me. So here's how I approached it. So the first thing to do is to just read a lot to kind of be informed about what's going on in your area of interest. And in terms of the proposal, be able to articulate exactly the state of the field and the state of the gaps in knowledge that exist, the gaps in possible techniques that exist that you could address. The only way to really be able to do it is to just read a lot and absorb a lot of the current research that's going on and try to figure out, okay, like this part I understand and I think the community understands, and then here there is a gap in understanding or a gap in terms of what was experimentally demonstrated, and this is something that they can address. So And I think that's really usually the process. Usually it's not that kind of a brilliant idea strikes you. It's that you think through a lot of the research papers that have been done, and then you say, okay, well, like this is the obvious next step. Sometimes you get an idea that's out of left field as well, and that's also great. So I think about it, and part of it is it's my personality, but I think about a proposal as an argument. And the argument is, well, like, here's why what I'm doing is important. Here's why it makes sense. Here's why I can actually do the things that I'm proposing to do. So I try to just explicitly think about it in terms of I'm making an argument. I try to signal that I know how to proceed with the project. So what I mean by that is both that I try to signal that I understand the field, and the way I did it is by talking about the problem that I'm addressing in a way that I thought made sense. And I also, to the extent possible, I didn't do it a lot, but I try to make sure that people understand, okay, like I've already done some work on that. I know how to implement whatever it is that I'm proposing to implement. And I can do it, basically, was the idea. And I think I want to emphasize again, there's just no substitute really in terms of actually doing good science, good engineering for immersing yourself in the literature and getting hands-on experience. This is something that you can try to fake, and definitely people do try to kind of fake it till you make it all the time. But to actually make progress, I think that's the only way. And the NSERC award committees try to basically see whether you've done it or not, whether you've immersed yourself in the field and understand what's going on. So I just argued that you can't really write a good proposal unless you're immersed in a specific subfield. And that kind of implies that it would be difficult to actually explain what a good proposal is, because you got to get into the nitty-gritty and actually say, okay, like this is the subfield, this is the gap in the literature, and this is how I'm addressing it. And I just argued the only way to do it is to actually understand the subfield. So what I'm going to do is I'm going to try to give you, I'll also give you my actual proposal, which is also kind of out of date now, but I'll also give you the proposal for what, Johannes Kepler might have written when he was proposing his model. So hopefully you know a little bit about it, but I'll give a brief explanation as well of what I think Kepler might have been saying he was up to if he were trying to get funded by the Canadian government. So we need to go back kind of a couple thousand years when people were trying to predict the motion of planets. And kind of people have been doing it for kind of various purposes, some more useful than others. So what people have come up with is that it seems like planets go around the Earth, but not quite. In fact, what it seems like is they go in this kind of shape. So this is kind of predictive, but not the best you can do. But this was the first idea. So let's imagine that the planet goes around the sun, except the Earth, sorry, except it doesn't quite go in a circle. It's that within that circle, there's those curls that go around like this. So those are called epicycles. And it turned out that you can just write down, okay, like this is the size of the epicycles, this is the size of the big cycle. And if you add the epicycles, you are able to predict the motion of the planet more accurately. And then you can add epicycles on top of epicycles and epicycles on top of epicycles on top of epicycles, and you get a model that's more and more accurate. in terms of predicting what's going to happen. And it's all kind of periodic, right? So this would be kind of the representation of what epicycles look like. So the problem with this kind of model is it's very complex, right? So there's lots of parameters. So each epicycle essentially is at least one parameter, so the size of the cycle. And the more epicycles you add, the more parameters you have. That comes with the benefit that it's more predictive. Now, one problem with that is, well, you wouldn't discover Newton's laws if you thought that the epicycles were the right model. So there is a problem there in terms of understanding the laws of physics. But there is also a problem where, like, you might say, okay, we don't really know why and how gravity works exactly. So maybe Newton's laws are not an improvement. But here's an argument for why that's not the case. So if you go with Kepler's model, and then from Kepler's model, you go to Newton's laws, then you can say, okay, unlike with epicycles, if I see an anomaly, like, for example, I see that the orbit is not quite what I expect based on what I know about the planets and based on what I know about Newton's laws, then, well, maybe the problem is not the laws. The laws are solid. Maybe the problem is that I don't know about the planet. That is how Neptune was discovered. Right? So people saw what looked like an anomaly in the orbits that were predicted using Newton's laws. And then they said, okay, well, like a planet would explain that anomaly. This kind of thing would not work with epicycles. With epicycles, of course, you would see anomalies, but you see anomalies all the time with epicycles. And the solution is, well, just add one more epicycle. The distinction here is that epicycles are not real, whereas Neptune is a real planet, right? So discovering that you need one more epicycle is not an interesting observation. Discovering that there is a planet that's unknown, that's affecting the orbits of other planets, and actually predicting, as has been done, okay, like if you look at that point in the sky at that point in time, you'll see it. Well, that's interesting. So this is all kind of against the background. Kepler is working against the background of the Copernican model, where it seemed like, if you actually model things as the sun is fixed and the planets go around the sun, then a lot is explained. But the Copernican model, of course, is not actually that accurate in terms of prediction, because the planets don't actually go in circles around the sun as it happens. It's more like ellipses. So if I imagine, and it's a little bit, anachronistic, but if I imagine what Kepler might have been thinking in retrospect, is he might have been thinking, okay, so the Copernican model with the circles is very simple. It's parsimonious. So that's great. But it's not accurate. And then the epicycles are really predictive, but they're really complex. So what one might think is, okay, like, can we do something that's a compromise between the two, where the shapes are more complex than circles, but not as complex as the epicycles? Right. So that might be the goal. I'm not claiming that Kepler thought exactly that, but this is kind of the premise of writing kind of the Kepler NSERC proposal, or the kind of thing that he might have written. So here it is. It's a one-pager. I wrote it. So enhancing the Copernican model for better predictive accuracy and new planetary discoveries, we called it. So here's, and I'll post a link to that as well. So here's what I'm trying to do here. So I'm trying to argue, okay, what I'm doing, well, what Kepler is doing is important. And I'm also trying to say it's interesting both for the prospective discoveries, but it's also interesting because, Copernicus just developed is strong, but you have the Copernican model, which people are talking about, and well, people are talking about it, so it must be interesting. And we're trying to develop it. And also people are using those epicycles. So we're trying to improve that. So we're situating the work in kind of existing work. And this is basically this paragraph. So I'm also trying to introduce kind of the idea that if it's parsimonious and accurate, we can enable the discovery of new celestial bodies. So I'll have a paragraph about that later. So here I'm trying to both just kind of as a self-contained document, just say, okay, this is what's going on. Implicitly, I'm also trying to communicate, okay, well, hopefully it's true. So I'm trying to communicate that I know what's going on in the field, right? So here I'm describing the epicycles and the Copernican model. So then I have a plan. So I'm saying we're going to explore geometric forms that are not just circles. So here's a hard part, right? Because the obvious question to Kepler is, well, different geometric forms, like, what do you mean? Like, either, and like someone might say, well, like, either you kind of already know what's going on, or you have no idea and you're just stuck and you're just trying this. So here, it's not a real proposal. So I kind of said, okay, like orbits that can be parameterized by a few parameters. And I said like e.g. conic sections. So conic sections, you might know, are ellipses, which would be a good idea. Also parabolas, which don't seem like a good idea. Well, like you might imagine kind of combining several parabolas into an orbit or something like that. Hyperbolas as well. Again, so some of those actually describe trajectories, just not like stable orbits. So here I'm saying, okay, if we have a proposed model, so I'm saying we'll collect some astronomical data and we'll try to validate the new models against the astronomical data. And here I'm specifying how, so I'm saying we'll just do least squares. I don't know if that's what Kepler did. So here I'm arguing, okay, so we can actually discover new planets. This might be a little bit weird, like maybe I don't, so I'll say like discovery of new heavenly bodies or something. So maybe like a particularly big asteroid or something. And here I'm basically outlining the idea of if we by identify, so I'm not going to say predictive limitations, I'm going to say inaccuracies. And here I'm arguing that it's impossible in an epicycle-based model. And it's not a very complicated argument, but again, I think it kind of indicates that I have thought about this a little bit and I kind of know what's going on. And finally, here I put a summary paragraph. You don't always have space for that kind of thing, but it turned out that I do. So yeah, and I have my references on the second page. So, okay. So all right. So that's my fake Copernican model proposal. So I also want to look at my actual proposal that got funded. So I'll briefly tell you about it. It's honestly not that interesting. It was a long time ago as well. But at the time, a recent paper was by Dalal and Triggs that came out and they were doing pedestrian detection. And this was before kind of the widespread adoption of neural networks. So this was with basically what's called handcrafted, hand-engineered features. So basically the idea was that at every square or at every location on the image, what we'll do is we'll compute the gradients and we'll compute the histogram of the direction of the gradients. So here what you see is kind of like a representation of what that histogram might look like with kind of, if you have a lot of gradients that are pointing in the same direction, then you'll kind of see the direction on the histogram. So the histogram is kind of represented as using kind of directions rather than using just columns. And then what they've done, the Lau and Triggs, is they just aggregated those histograms of gradients across the entire image, stuck them together into one big n-dimensional feature vector, and then they classified them with SVMs. And that worked better than the state of the art at the time for detecting pedestrians in images. So on the other hand, there was this paper by Zhu and others that showed that you can compute these histograms of gradients locally rather than across the entire window. So what I mean by that is rather than do just one n-dimensional vector that's just all the histogram of gradients concatenated, what you can do is you can select, so in this case using AdaBoost, so select which areas in the image to compute the histogram of gradients on, and then basically adaptively learn which squares on the image and at which scale to compute the histogram of gradients on, and then you basically classify the histogram of gradients in a kind of cascade where like one after the other. And that was shown to work much faster, so it's more efficient than computing all of the histogram of gradients and then sticking them together into one huge feature vector. Here, the feature vectors are quite small, and you iteratively classify those, kind of classify this location, classify this location, classify that location, until you're sure that it's a pedestrian. That's faster as well. So my thought was at the time, not so much about the speed as much as about if you do it this way, then what you're doing is you're basically classifying the entire thing based on a fixed template. So there's no opportunity, I thought, to really figure out, okay, I want to model the shape of, so pedestrians are all the same shape, so that's fine. But if you have variation in shape, it's harder to model the shape because it's all fixed. On the other hand, I thought that this kind of idea of figuring out where to look for the histogram of gradients allows you to possibly model shape better. So that was kind of the intuition. Okay, so, and kind of part of it is the Juel paper allows you to go into really fine scales or really coarse scales. So there's more flexibility in terms of modeling the shape than just the fixed template. So that's the idea that I wanted to present. Here are the things that I paid attention to. So obviously explain the idea as much as space allows, give as much context. Again, as space allows, you only have one page. Wanted to give evidence that they know where to start with the project. In fact, I said that I already started, and try to explain why the project is interesting. So separately from that, I also wanted to just kind of communicate, again, like with the Kepler project, communicate that I know what I'm talking about and that I understand kind of the sub area. Whether I did or not is maybe questionable, but people thought so at the time. Here's what I wrote. So it's part-based detection using histogram gradients. So this is, I did not edit this, so this is what they sent to NSERC. So here, this I would actually leave out, like, I'm not going to convince anyone that object detection is an important problem in computer vision with this statement. Maybe not useful. So this, as an assertion, it's not that interesting, but saying that my goal is to find good feature for object modeling and algorithms for part-based learning and detection, well, I got to say it at some point. So here I'm just, again, saying what I'm going to do. In the course of the research might have been a waste of space. And I would not say it today. So here I'm saying I hope to advance the understanding of why and when the histogram gradients feature works. Develop an automatic parts learning and detection algorithm that is particularly suitable to detect object class parts using HOG, but is also generally applicable. And to improve results in 1 and 3. That's the papers that I told you about. So here, kind of, the reason I said this is not kind of to look good. This is actually what I wanted to do. Is I wanted to understand. I still kind of am curious about this. I wanted to understand why this kind of feature works. At the time, it was new and it was kind of mysterious. I think it's still a little bit mysterious that it works so well. And here, so I kind of focused here both on understanding and also just developing an algorithm. And well, the reason I said I'm interested in understanding is that I was, but, and, I think it's good, but I think really depends on what you're proposing to do. Maybe you want kind of just something that works. Maybe you want to understand, maybe you want to kind of explore why it works. Separate questions, both valid. So here I'm just giving the context. So I'm saying, okay, so Dalal and Triggs demonstrated this. And then Ju, Alvedon, and everyone and friends said that they were able to do the equivalent using kind of local HOG features. So here I'm doing something that's a quite usual thing, I feel, and I actually did that in the Kepler proposal as well, right? So I'm saying, well, like, we'll take this and we'll combine them. And it's like an extremely usual kind of research pattern. And, part of it is that it works, but part of it is also that it's kind of easy to argue for. So here I'm kind of arguing that, okay, so maybe kind of part 3 would allow for modeling of more complex shapes. So more complex, what does it mean? Well, it has parts to it. So I'm saying, maybe we can do parts-based detection because, we're focusing on this area or that area of the image. So here I'm proposing what I think did not work out, actually. So I want to modify the object in 3. And what they had done is they were just, looking for the best feature at the best scale. And my idea was, oh, maybe we do explicitly detecting of parts first, and then we'll guide the fact that we know where the different subcomponents of the shape are in order to select good features. So here I'm proposing another thing, so just use more features than HOGs. So nothing kind of non-obvious, and that's kind of the best idea that I have. And here I'm signaling, okay, like I've implemented the algorithms and expect research progress very soon. That was true. It turned out that this particular project didn't really work out. So that's this. Yeah, so thank you for listening.